In this program, we will describe an investigation of a school in North Dakota where elevated radon levels were determined during an initial radon survey. This will illustrate some of the steps that could be taken by school administrators and maintenance personnel, as well as how a field investigation can occur and the conclusions reached with recommendations for remediation. This is an auxiliary video to a video titled Dealing with Radon in Schools. It is suggested that that video be reviewed prior to viewing this case study for a more comprehensive review of the radon response process. As part of its ongoing effort for reducing indoor radon exposure, the North Dakota Department of Environmental Quality has been assisting North Dakota schools by testing their facilities for radon. In this particular school, a number of locations were determined to be above 4 picocuries per liter. The first step was to review when the tests were conducted to ensure they measured conditions during the school week and during the winter. The tests were conducted between February 19, 2019, which was a Tuesday, through February 22, 2019, which was a Friday, so the testing period was correct. A total of 20 locations were tested at the same time, with 2 locations having duplicate measurements meeting the 10% duplicate requirement. In one unexposed, blank device was deployed meeting the 5% blank requirement. Duplicate pair 1 and duplicate pair 2 had relative percent differences of 17% and 2% respectively, which is well below the maximum 36% for devices with average results in excess of 4 picocuries per liter. The blank, unexposed device had a reported value of 1 picocurie, which is within tolerances. Consequently, confidence can be placed in the results obtained from the initial survey, and an investigation was appropriate at this point. A diagram of the school was developed. As can be seen from the diagram, the school is primarily at grade, with a basement area located under the stage and band room. 2 offices are located in the basement, with the balance of the lower level being storage rooms and locker rooms. The results from the laboratory were transferred to this diagram to determine survey completeness and potential localized radon pockets. In evaluating survey completeness, all classrooms, music rooms, offices, lounge, libraries are to be tested that are in contact with the soil or directly above earth and crawl spaces. Storage rooms, locker rooms, and bathrooms are not tested due to low occupancy. One can see in this case that all requisite rooms were tested, including the boiler room, which was tested since the maintenance person had an office in that location. In viewing the data, one can see there are higher levels in the southeast lower right-hand corner of the diagram portion of the building. The basement level also had elevated levels, as would be expected. But also the western portion of the building had a large cluster of elevated levels, indicating that they had similar radon entry phenomena for all of those rooms. A walk around the outside of the building revealed the fresh air makeup vents had been boarded over. The current maintenance person was unaware when this had been done, as it was well before his assignment to the school. However, judging by the condition of the plywood, it would appear that they had been boarded up for quite some time, and major work would be required to remove those and ensure that the dampers were working. A week prior to the field investigation, continuous radon monitors were deployed in 4 locations. The data showed that although average radon levels are different from room to room, as was borne out by the initial survey, there were no dramatic changes in the radon from daytime to nighttime, as would be in the case of an energy management system existing that would provide fresh air, outdoor air during the day, but not at night. This lack of change in daytime to nighttime exposures is understandable in light of the fact that the fresh air makeup had been disabled by the application of the plywood boxes. Also, judging by the varying condition of the plywood, variation of room averages from room to room may be explained by different degrees of leakage of the fresh air through these boxes. The next step was to investigate the structure. Fortunately, a set of drawings of the building was located. These provided several insights. There are two tunnel systems within the building. One impacting the West End, where there was a large cluster of rooms with elevated radon, and another tunnel running from the basement access door around the north and east perimeter of the building. The West Tunnel has an access door located in the front offices, where the other hotspot for radon had been found. Upon closer examination of the drawings and inspecting the tunnels, it was discovered on the tunnel on the west side provided both a pathway for utilities servicing the wall-mounted heaters in the room, but also there were formed openings under the floor under the unit ventilators that allow air from the tunnel up into the room. In addition to this, there were two inactive air handlers on either end of this tunnel, whose original purpose was to draw fresh outdoor air in, heat it, and supply it to the tunnel where the fresh air could pass up through the intentional openings beneath the unit ventilators. In this manner, fresh air would be provided to the classroom. It was learned that these air handlers had been deactivated as a part of a renovation where additional power was needed from an existing power panel for other purposes. Also, a new roof structure was constructed over the building to where the intake of these air handlers are no longer able to obtain fresh outdoor air. It is recommended that these air handlers be reactivated with ducting routed to the outside for the provision of outdoor air to the West End classrooms as originally designed. With regard to the east end of the building, the tunnel is not designed to convey fresh air to the rooms. Instead, fresh air was to be provided by the unit ventilators whose outside fresh air intakes had been plywooded over. Radon grab samples taken in the east tunnel confirmed elevated radon levels within the tunnel. The east tunnel provides a pathway for electrical as well as utility lines to the unit ventilators above the tunnel. An inspection of the unit ventilators showed large gaps around utility lines leading up to them, thus allowing radon in the tunnel to migrate up into the unit ventilators and hence into the occupied rooms. Assuming that the repair of the unit ventilators to where they could once again provide fresh air would be a major task and dependent upon funding, the option of a tunnel depressurization system was explored. In this approach, a system would be installed to draw air out of the tunnel and exhaust it outside with the goal of preventing or reducing the radon-laden air from within the tunnel from entering the occupied space above it. To test this approach, a temporary system with the assistance of maintenance personnel was installed and a continuous radon monitor deployed in the southeast office to determine results. At appointed and recorded times, the maintenance person turned the temporary tunnel exhaust system on and off. The results of the hourly measurements were then correlated to operational periods of the temporary exhaust system. The results clearly indicate exhausting the tunnel dramatically reduced radon from within the occupied space. It should also be noted that the exhausted air was musty, and the person occupying the room during the trials indicated that the air within their office felt much fresher. It is recommended based upon this experiment that unless the unit ventilators can be repaired to where fresh air is again provided as originally designed, that a tunnel exhaust system be permanently installed with the exhaust above the roof. Furthermore, gaps around utility piping servicing the unit ventilators should be sealed with foam to minimize the loss of interior conditioned air. The third area of consideration was the basement area under the band room and stage. This area had two offices with elevated radon levels, and there is no ventilation system that serves these areas that could be used for radon reduction. Consequently, the approach of adding an active soil depressurization system was evaluated. Active soil depressurization is a common technique in the radon mitigation field where a hole is cored through the slab in an appropriate and convenient location. The hole dug out, a pipe connected to it, and routed to an attic space or outdoors where a constantly operating radon fan is installed with its discharge routed to an atmosphere where it can harmlessly discharge radon collected from under the slab. This discharge should be sufficiently far away from building openings and air intakes to prevent re-entry into the structure. This approach is explained in greater detail within the parent video to this case study. To evaluate the efficacy of this approach, a shop vacuum was utilized to simulate an active cell depressurization system. A hole was drilled at a location that would be suitable for a permanent suction point. In this case, the storage closet under the stairs was selected. Smaller pilot holes were drilled in the lower level classroom and the office as test points. A hose from the suction side of the shop vacuum was connected to the proposed suction hole under the stairs and turned on and off for short periods of time. Pressure differential measurements between the subgrade and the interior of the subject rooms were made using a micromanometer capable of measuring in thousandths of an inch. Measurements were taken with both the shop vac on and off so as to identify impact at given pilot holes. This diagram shows the results of the active cell depressurization simulation. As can be seen from the data, a suction point located under the stairs will impact both rooms of concern, which is good. Airflow measurements were also taken as a means for determining fan and pipe size requirements. Routing for the ASD system was determined to be from the suction point in the storage room under the stairs to the attic space by running it up through the unoccupied space behind the stage, into the attic and through the overroof. The radon fan would be located in the attic space and performance indicator on a portion of pipe visible from within the stage area. Returning to the west end of the building, diagnostics were also performed to determine if an active cell depressurization system could be utilized in lieu of activating the two forced air units to restore fresh air makeup. Similar to the diagnostics performed in the basement, holes were drilled in the slab for both applying a simulated vacuum with a shop vac, as well as pilot holes for measuring impact of the vacuum at various areas and locations within the wing. As can be seen from the data, there was no impact of a vacuum applied from one room to an adjacent room, and no impact from one room to a room across the hallway. And this was done at vacuum applied at two different possible suction point locations. These results were not surprising, as the soil encountered when the holes were drilled was extremely fine and not conducive to lateral airflow. These results indicate that if an active cell depressurization system were to be employed, an individual system would be needed for each classroom within the West Wing. Based upon these findings and the presence of the two fresh air makeup forced air units that presumably are operable, it would be preferable to reactivate those units as previously discussed. This will reduce radon but also improve overall air quality within these rooms. As can be seen, this particular case study was a gnarly one. Fortunately, most schools, at least more recently constructed ones, have a lot more options available if their heating, ventilating, and air conditioning system is reasonably up to date. But this case study does point out what can happen if HVAC systems are not maintained or if they are modified or disabled for energy conservation reasons or given a lower priority during a renovation. We trust this case study, along with the parent video dealing with radon in schools, was informative. And if you have any questions, please do not hesitate to contact your state radon program manager or sending me an email. Thank you.